Hi guys, so in this video we're going to be talking about L'Hopital's rule, which is section 13.6 of chapter 13. So basically what L'Hopital's rule says is the following. If you're finding the limit as x approaches a value c of a rational function f of x over g of x, and after you plug in c, you get 0 over 0, or if you do the same and you get infinity over infinity, positive, negative infinity, positive, negative infinity, then you can apply L'Hopital's rule, which is that the limit as x approaches c of f of x over g of x is the same as finding the limit as x approaches c to the derivative of f of x over the derivative of g of x. Now, if you keep getting 0 over 0, for example, then you can do actually the next derivative and so forth. Okay, very well. So first we're going to look at example 13.30, and they say find the limit as x approaches 1 of that function. Now notice that if we plug in 1, what do we get? We would get 1 minus 1 plus 0 over 1 minus 3 plus 2. And this obviously gives us 0 over 0. So we can apply now L'Hopital's rule and do the derivative of this function in here. So we're going to get minus 1 plus 1 over x over 3x squared minus 3. And then we can just do the same limit. So limit as x approaches 1. So that's just substituting x with 1. And don't forget the proper notation with the parenthesis. And then we're going to get minus 1 plus 1 over 1, which is 1 over 3 minus 3. So notice that we again we get 0 over 0. That means that we can apply L'Hopital's rule once more. Minus 1 over x squared over 6x. And then we do the same thing again. Let's find the limit as x approaches 1 of this expression, negative 1 over 6. Very well, so next we're going to do example 13.29, and it says for each limit, use your graphing display calculator to conjecture a result, then find the limit using L'Hopital's rule. So I'll leave the GDC part for you guys as practice. I'll just do finding the limit using L'Hopital's rule. So for A, if we have limit as x approaches 0 of x over 1 minus e to the x. Notice that if you plug in 0 there, you're going to get 0 over 1 minus 1, which again is 0 over 0. So let's do the derivative of the inside, because now we can apply L'Hopital's rule. So this is going to be 1 over minus e to the x. Find the limit of that as x approaches 0, and we're going to get 1 over minus 1, which is negative 1. Okay, so now we'll take a look at B. So for B, they ask us to find the limit as x approaches pi halves for secant of x over 1 plus tangent of x. So what I suggest you guys do here in general is rewrite this in terms of sine and cosine. So secant we know is 1 over cosine of x, and this would be over 1 plus sine of x over cosine of x. And then let's plug in pi halves. So what do we get if we plug in pi halves? So it'll be 1 over 0 divided by 1 plus 1 over 0. Okay, so notice that this is undefined and this is undefined here and this is undefined there. But think of approaching the value of 0 from the left in these two cases. So what happens when you approach the value 0 from the left and 1 is divided by that very tiny negative number? Well, you're going to get negative infinity. And the same thing here, if you approach it from the left, you're also going to get negative infinity. So negative infinity plus 1, we can just ignore the 1. So this is negative infinity over negative infinity if you approach it from the left. What happens if you approach it from the right? Well, you're going to get positive infinity over positive infinity. So that means that we can apply L'Hopital's rule. So then let's find the derivative of the inside here. So the derivative of secant is secant times tangent, and the derivative of 1 plus tangent is going to be secant squared. So notice that this can cancel out with one of these. So we get tangent over secant. But before you plug in, because we're doing the limit as x approaches pi halves, before you plug in pi halves, make sure you rewrite this in terms of sine and cosine. So this would be sine of x over cosine of x, and secant is 1 over cosine of x. So notice that this implies that we can cancel out the cosines, and we're just left with sine of x. And if we plug in pi halves, we know that sine of pi halves is equal to 1, and that would be the limit. Okay, so now we're going to focus on letter C. And the first thing we're going to do is plug in 0, right? Because it's the limit as x approaches 0. So notice that if we plug in 0 here, we're going to get e to the 0 plus 0, and this to the power of 1 over 0. And this doesn't make any sense. For now, we cannot apply L'Hopital's rule because it only applies to situations where we get 0 over 0. And that's not the case here. But we don't have to give up, because if you have Euler's number, then we can do a trick using natural logarithms. So notice that we could rewrite this expression as f of x is equal to e to the x plus x to the power of 1 over x. And if I do the natural logarithm to both sides of this equation, natural logarithm of f of x equal to the natural logarithm of this expression. Because I have a natural logarithm here, we can send this exponent to multiply. So I'm only going to focus on the right-hand side for now. So this is going to be equal to the natural logarithm of e to the x plus x over x. And now what I'm going to do is that I'm going to find the limit of this expression as x approaches 0. So let's move on here to the left. So what would be the limit as x approaches 0 of this expression, right? Natural logarithm of e to the x plus x over x. Well, all we have to do is plug in 0 and see what we get, right? So we would get natural logarithm of e to the 0, which is 1 plus 0. So that stays natural logarithm of 1 over 0. But natural logarithm of 1 is 0. So this is the same as 0 over 0. Therefore, we can apply now L'Hopital's rule. So we do the derivative of this, and we're going to get 1 over e to the x plus x times the derivative of the inside, which would be e to the x plus 1. But this is the same as e to the x plus 1 over e to the x plus x. So if we apply the limit to this, the limit as x approaches 0 to this expression here, we're going to get e to the 0 plus 1 over e to the 0 plus 0, which is going to be 2 over 1, which is 2. But we're not done, right? This is just the limit of the natural logarithm of f of x. That would be the result of doing the limit of this as well, right? So let's write that over here. We would say then that the limit as x approaches 0 to the natural logarithm of f of x equals 2. Therefore, we can then say that because this is the limit as x approaches 0 to the natural logarithm of f of x, that means then, or that implies that the limit as x approaches 0 of f of x is going to be e to the 2. All right, so that means, because we said that f of x is equal to e to the x plus x to the power of 1 over x, that means then that the limit as x approaches 0 of e to the x plus x to the power of 1 over x is equal to e to the 2, which is approximately 7.38. And this rounded to 3 significant figures.